So now we would like to extend this further to cover other important programming language constructs like the array reference, like this. A x equals a times a of b times 2 plus 9 plus c. So now, does this grammar support an expression like this? Doesn't even have brackets anywhere, right? So it doesn't support this. So we need to support array references. Where do you think we should add this? At which level? Which level? Yeah, it's a factor, right? Here in this expression, this array reference, this thing is what? Is a factor, right? So we have two terms. This is term, and this is another big term. And this term consists of two factors. Factor number one is this. Factor number two is the array reference, which clearly has an expression in it. So an array, between brackets, you can have an arbitrary expression. So it will be easy to just say an array reference is what? So what's this? What's this? What's the A? This is an identifier. So this is an identifier. And then brackets. And what's inside? An expression. Okay. So there is one more thing that we need to support, which is function calls. Like if you have a function like fx of a, b, 5 times a plus c, whatever. So if you have this is enough. So if you have a function call like this, how would you represent it? So what's this? This is an identifier. And what's this? Okay, so I can see the parentheses. So identifier, and I see the parentheses. But what's inside? What's that?
Comma-separated expression.
Yeah, exactly. So these are comma-separated expressions. So each one of these is an expression. You can put, this is one argument, and the other argument could be 5 or 6 minus b times d. Yeah. Expression, comma, expression. So is it limited to only 2? So we want it to be unlimited. We would like to have an unlimited number of arguments for the function. How would we implement this? Well, let's call this an expression list. Then we need to define the expression list. How would you define an expression list such that the number of expressions in the list is unlimited? What's the only way of defining this such that the number of expressions in the expression list is unlimited? What's that? Yes, recursion, exactly. So we need recursion in order to define an expression list with an unlimited number of expressions. So we can say it's expression list, comma, expression. Is this enough? What do we need for recursion? Yeah, we need a base. And here, let's say the base is expression. This means that we'll have to have at least one expression. Of course, here, if you put epsilon, it's not going to work. But you can accept the epsilon with this little bit of manipulation. In fact, you can just OR this whole thing with an epsilon, right? So you can, for example, you can introduce something that you call x, and this is x, and then x is either this definition of expression list or epsilon. So this is one way of doing it, but in fact there are more elegant ways of doing it, but we don't care. It's not the point at this point. But I'm just trying to show you how to allow an empty expression list. But let's assume that the expression list will have at least one expression in it. And of course, what's the problem here with this definition? This is left recursive. So we can do this in the right recursive form. Left recursion elimination. What does left recursion elimination give us in this case? Expression list is what? Where is the beta? Expression. Then concatenated with something else like expression list prime, where expression list prime is what? Where is the alpha? So we are recursing on expression list. The recursion is on expression list. This is the alpha, and this is the beta. So this is comma expression list prime. Okay. So now we eliminated left recursion, but in fact this is not the point. Here we have a serious problem in this grammar. Is this grammar LL1? It clearly is not LL1. Why not? What's that? Yeah, clearly the identifier is a common factor. This can start with an identifier, this can start with an identifier, and this can start with an identifier. So you have three alternatives that can start with an identifier. So clearly this is not. Now we cannot say that the language is not LL1. We can say that this grammar is not LL1. Yes?
Shouldn't at the very bottom of the expert list, shouldn't there be another option so that we can?
The epsilon, yes. You're right. Okay. But now, why isn't this grammar LL1? So it has this identifier as a common factor. Now, for cases like this, there is a very quick fix, which is in fact, you can just do factoring. You just take the the common factor, take it, and you do what we call left factoring. It's just like factoring in algebra. So how would you factor this? Or let's use a factor. Okay. So we define factor as number or expression, or we take the common factor, which is identifier. So it's identifier concatenated, then this is concatenated with something. This is something we call it whatever. You call it factor prime. So it's just like, concatenation in this, in grammars is just like, or in formal languages, concatenation is just like multiplication. So here it's like, this is multiplied by what? Concatenated with what? This is identifier concatenated with epsilon. And this is identifier concatenated with this thing. So just like multiplication. So factor prime is, what's factor prime? Epsilon or, expression, or this expression between brackets, or expression list. So this is left factoring. This is what we call left factoring, and it's just like factoring in algebra, where you take the common factor, and then this factor prime has the different non-common parts of the of each alternative. So the common is ident. What is not common is epsilon or bracket expression or parentheses, expression list between parentheses. Okay. So now here it may look like we can just take any grammar that is not LL1, and we can do left recursion elimination and left factoring and make it LL1. Well, this is not true. There are grammars that cannot be converted into LL1 grammars, like this grammar, for example. So grammar like S is A or B, and then A is A or A, B is B or B. So if you try to do whatever left recursion elimination or left factoring, you're not going to be able to convert this into an LL1 grammar because if you have so how do you derive from this? So you derive S is either A or B, and then when it's A, you can keep doing A parentheses. You can put as many parentheses as you want, then you substitute an A. So if you have a string like this, in fact, we are done. So if you have a string like this, and a string like this, okay, and you are trying to parse this string, and you are seeing open parentheses, will you know which one to substitute? Whether to substitute. So in the very beginning, you have an S, and you're trying to decide, should I go for an A or a B? And you're looking at this. It's not going to tell you whether to substitute an A or because this is valid for both A's and B's. So this is a grammar that you cannot convert into an LL1 grammar. This means that this language is not LL1. So this language is not LL1. Now this is a subtle concept that we need to understand very well. When we say that a language is not LL1, this means that you can never find an LL1 grammar for it. But when you say that a language is LL1, this means that there exists at least one LL1 grammar for it. So the language that is defined by the classic expression grammar, the classic expression as defined by the classic expression grammar is an LL1 language, but clearly there are non-LL1 grammars for it, and this is one of them. This grammar is a non-LL1 grammar for an LL1 language, but we managed to convert it into an LL1 grammar because the language is LL1. Okay, so a language is LL1 if it has at least one LL1 grammar. So if you can find at least one LL1 grammar, in other words, for an LL1 language, I may give you a grammar that is not LL1, like the original form of this. It's not LL1. Like this, left recursive form is not LL1. But if the language is LL1, then you will be able to convert the grammar into an LL1, into an equivalent LL1 grammar. Just like regular languages. We defined a regular language, or we can write it here. How do we define a regular language in terms of regular grammar? A regular language, or a language is regular if it has what? At least one regular grammar. So in other words, a regular grammar may have many, many equivalent grammars that are not regular. And an LL1 grammar can have many, many grammars that are not LL1. So here, the concept here is the distinction between the property of a language, whether a language has the LL1 property or not, and the concept of whether a grammar is LL1 or not. Okay, any questions on this? So, so these subtleties are important in this course. This is a theory course, and such subtleties are important. Any questions? Okay, so this is this is what we mean by LL1. LL1 language and LL1 grammar. Well, one more thing. So we have, again, I draw this hierarchy. So I have regular languages, and then I have LL1 languages. The set of LL1 languages, and these are all subsets of context-free languages. Okay, so the set of context-free languages is the set of languages that can be represented by or generated by context-free grammars. A subset of that is those grammars that are LL1 that can be parsed using the LL1 parsing technique, or that satisfy the LL1 parsing conditions that we just had on the board. And a subset of that is regular languages. Regular languages is a very very a very simple subset of context-free languages. So every regular language is context-free, and it's also LL1. Every LL1 language is context-free. Yeah.
Are we going to be exploring any other grammar types besides L1, RR1?
Yeah, so there are LR1, but we will not study them in this course. So there is like a set LR1, but we will not be studying this in this. So there is LR1. LR1 languages that can be parsed using the LR1 parsing technique, which we do not study in this course, but we study in the compiler course. So LR1 is a more powerful parsing technique that parses a larger set of languages.